Welcome to the Creo Parametric 7.0 product update around multibody design. My name is Martin Neumueller, and as a member of the Creo product management team, it's really a pleasure for me to show you the highlights of the multibody capabilities that we introduced in our latest release of Creo Parametric 7.0. The multibody project was one of the three big main development initiatives for Creo 7. And as such, there are a lot of new things here to show in the product and to discuss around the benefits and use case support it brings to all Creo users. Let's start with clarifying what we mean when we speak about bodies and multibody design. So, what is a body? A body is a new concept and object type in Creo Parametric 7.0 to separately design, visualize and manage geometric volumes in the part design environment. In earlier versions of Creo Parametric, a part is essentially treated as a single body part, as all solid geometry in a part is considered a single lump of geometry of the same type, material and properties. With Creo Parametric 7, you can create parts that contain one or more bodies, which holds separate geometry that's not automatically being merged with geometry of other bodies in the part. In addition, bodies can carry many specific characteristics, such as different names, appearances, materials, or parameter, as illustrated here. This provides more efficient and flexible part design workflows by making use of multiple bodies that might be created within the part itself or brought in from external models. Bodies can then interact through operations such as, for example, Boolean merge, subtract, or intersect operations, as well as a split operation that would split off a portion of a body into a new body. A multibody part can be the desired end result of the design workflow, meaning that multiple bodies are preserved in the final design. Note that multibody techniques can also be applied during a design workflow, even if bodies are merged or consumed in the final design, then resulting in a single body model. There's a broad range of use cases where multibody design can benefit the design process. Firstly, it enables advanced design workflows such as generative design, simulation-driven design, and design for additive manufacturing. As those will be presented in greater detail in other presentations within this virtual LiveWorx event, I will just briefly touch on those and highlight the multibody related aspects. With multibody design, you can use bodies to create volumes of overlapping solid geometry and manage different geometry types. This is valuable in generative design, where you can designate bodies to design, manage and visualize input geometry for different purposes, such as starting geometry, preserved geometry, and excluded geometry. Also, the output of the generative design process can be brought into the part design environment in form of new bodies. Let's have a look at the workflow in the following video. Here an illustration of the workflow. We have our input geometry structured in 5 bodies. We have one that we call the initial design base, which is a blue support bracket here. We have the envelope geometry in the body called start geometry, and we have 3 screw bodies. And within the generative design environment, those bodies can then directly be used as input for the various categories that we need for generative design setup. For starting geometry, preserved geometry, and excluded geometry. Once loads and constraints, design criteria and goals are specified, the generative design engine then starts the optimization, resulting in new geometry. That generative design result created by the generative design process can now be brought into the part design environment. That happens in form of a new body, because you want to manage that result geometry separately, in particular as it's actually not BREP but generated tessellated geometry. And then another new body is created by a following geometry reconstruction process, which is used to reconstruct new B-rep geometry from the tessellated optimization result. Bodies can then be marked as construction bodies, and we'll talk much more about that later. And of course, we can merge bodies together where we want or need to do so. In Creo Parametric 7, you can design multi-body parts and then use them for flow simulation in Creo Simulation Live. You can create multiple bodies for different design purposes, again, such as for the fluid cavity and solid geometry bodies respectively, while staying in context of the part design environment. You could also drive your design through the optimization of the cavity body and then add material to create the surrounding solid part, and then use Boolean subtract operations during the design to remove mutual body interferences. In this video snippet, we brought our model to Creo Simulation Live, told it to use the cavity body as fluid domain for the simulation, and can then visualize the fluid flow simulation. And as we have defined the interacting volumes as bodies, we could now of course very easily use a move feature to move the plunger body up or down to represent and simulate different opening scenarios. The multi-body design concepts in Creo Parametric 7 also support additive manufacturing related design workflows in two major areas. The first area is lattice creation, as design in the context of additive manufacturing typically includes considerations around lattice creation and optimization. So here we want to leverage the multi-body concept of Creo 7 for the lattice definition, where you can now apply a lattice to a selected volume defined by a body, or even create the lattice geometry in a new body. In addition, we can leverage other body aspects for 3D printed parts. Body color would be one example of that. Let's have a look at both in the following demonstration video. You can now either design this part as a multi-body part up front, or as we see it here, you can make use of the split operation to split a single body part into two bodies. Let's give the inner one a new yellow color and make it a bit more transparent. You can now easily leverage the predefined body volumes to specify the volume areas that are intended to be filled with lattice geometry. The lattice feature can replace geometry of a selected body with lattice geometry, or create lattice geometry in a new body. Beyond lattice creation, multi-body capabilities further enrich additive manufacturing related workflows through the ability to perform a clearance validation between bodies, to assemble a multi-body model in the 3D printing tray, and if you work with a 3D printer connected through materialized build processes, you can define printing strategies by assigning different printing and build profiles to individual bodies. That means you can, for example, vary the laser power or other parameters when printing the lattice body versus the solid body. The second set of use cases enabled by multi-body design capabilities relate to the design of multi-material parts. This could be, for example, multi-material 3D printed parts or injection molded multi-material parts. Here we have an example of a multi-shot injection molded part. It's an electronic device housing of a harder plastic material combined with these yellow rubber overmolds that are required to seal connector ports to make them watertight, for example. When designing these multi-shot multi-material injection molded parts, you can assign material per body. This allows you to combine the design of the main piece created by the first shot in injection molding with the design of the overmold piece for the second shot in injection molding within the same part context. This makes the design of injection molded multi-material parts easier, where you can take advantage of a broad range of new capabilities. So first of all, you can design, manage and visualize the bodies in the same context. Here we have the housing body and the overmold body. You can set the appearance and assign a color to each body, as in the example here, where we colored the main body in blue and the overmold in yellow. You can assign material per body, and when you do so, this will override the body's default assignment of the part master material. Note that this capability can be controlled via a new configuration option called Enable Multi-Material Model. Reuse design intent and body definitions captured in user-defined features. When you place a UDF with the advanced reference configuration workflow, you can map each body reference to an existing body in the model or create a new body on the fly. You can use cross sections and define hatching per body, and if a body material definition includes the reference to a cross-hatching pattern definition, then you can choose use hatch from the part to apply the hatch pattern according to the material of the body. In addition, you can perform body interference and clearance checks within a cross-section or across the entire part. And finally, you can use data sharing to prepare various flavors of reference parts for mold design. Overall, Multibody can ease the design of injection molded multi-material parts significantly, avoid the complexity of dealing with assembly objects and external references, and instead use a single model with multiple bodies. Let's move on to the third benefit category of Multibody capabilities. This is going to be the biggest part of my presentation, where I want to show you in detail how these new capabilities can increase usability and productivity for aspects of general design workflows when designing multi-body and even single body parts. As we have seen before, working with multiple bodies can already increase usability just by the fact that you have more visualization flexibility and can freely hide and show geometric volumes as needed. Beyond that, using bodies can also ease and accelerate design tasks due to the power of booleans and split operations for bodies. For example, they can help to perform local or partial operations. The demo shows a situation where we want to only shell the lower portion of this part. We can now either design the lower and vertical geometric features as two bodies, or simply split the body into two as shown here. We apply a yellow appearance to the new body to better distinguish it, and can then invoke the shell command that previously shelled the entire part geometry to easily now only shell the gray body. This localized the shell operation as required. Of course, we can merge the yellow body back into the gray body at any point in time of the design to get back to a single body model. In addition, you can easily design and optimize subtractive geometry in the part context using multi-body concepts. This is beneficial in applications and use cases such as in the design of hydraulic manifolds or fluid cavities in general. You can create solid bodies representing cavities or subtractive geometry in general in your design, and then use the Boolean operation body subtract to get to the final geometry. Let's have a look. In this demonstration, you see the geometry of our main part in this transparent yellow color, along with the guiding curve that we now want to use to create a cooling channel. As we start defining the sweep feature, you see that the geometry it creates would be merged to the existing geometry by default. In this case, though, we would like to design the cavity as a separate body, and therefore check the Create New Body option within the Body Options panel. Let's color the new body containing the subtractive geometry in blue. It will later be used to create the cavity in the main body. As you can see, the representation of the cavity as a solid body during the design process already provides more flexibility in visualizations. Not only can you apply appearances to bodies and independently show or hide them, also cross-sections support the body concept with a broad range of new capabilities. You can, for example, easily visualize body interference areas within the cross-section in a separate interference color. The red interference area will of course disappear when you remove the interference by subtracting the body geometry from each other. By default, all solid bodies contribute to the volume and mass calculation of the part. As you can see here, we get a total mass of 6 point something in our report, and at the end of the report we see the contribution for each of the bodies, the main body and cavity body, listed out separately. But would you want that for a body representing subtractive geometry? The answer is typically not, right? We therefore introduce the concept to set a body as construction body. Doing this will turn its icon into a dashed icon to indicate its construction nature, and it will automatically ignore and exclude the construction body from total mass calculation, global interference and clearance, drawing repeat regions, material reporting, and from some other downstream workflows. As you can see here, the construction body is no longer being considered in the mass calculation, as it doesn't contribute to the total mass any longer. Beyond the blue cavity bodies, this design made two additional uses of the multibody concept. First, the green body is used to create the pocket cutout that another part will slide into. This body could be created within the same part, or for example be brought in from an external part, then be positioned with various methods, and then be subtracted from the main design part to create the pocket. The second additional use of the multibody concept in this model here was to help getting to a required reference geometry in a quick and most efficient way. Here, of course, we needed to create that curve that guides the swept cavity shape. And the easiest and fastest way to do this is to create two construction bodies that are then intersected with each other. Here you see the refinement of these two bodies. So the multi-body concept allows us to do that with the regular solid modeling tools in an intuitive and very familiar way, eliminating the need to switch to surface and quilt based tools and workflows for these situations. And finally, the intersection of these two bodies now allows us to use the intersection edges as the guiding curve for our sweep. After we derive that curve, we can of course get rid of these two tool bodies, helper bodies that we used to construct this geometry. You can also create and use bodies that are intended to act as modification tools to change geometry in other design bodies. The following example illustrates this, using the workflow to create the grooves in that yellow plastic part. Here we have our design part, where in the following we want to create grooves in that design part as we had seen on the previous picture. There are various workflows to do this. The fastest and most obvious one that we want to illustrate here makes use of a second body that will be used as a tool body to modify the geometry of our design. We start with creating some geometry and tell the system to put that geometry into a new body, which is this gray body called body 4. And as the geometry in that gray body is now regular solid geometry, we can continue to use regular solid modeling features and commands to refine that body, like creation of chamfers, or for example also mirror or pattern it, as in this example. We then trim the gray tool body with a certain offset from the top surface contour to finalize our tool body. This example here shows well that a body in Creo Parametric can actually consist of disjoint geometric volumes. And finally, we subtract the tool body from the yellow design body, which results in the desired grooves. So I sometimes get the question, what is the advantage of the multibody concept versus using the previous concepts of using quilts or surfaces? To answer this, I should probably first clarify that we are not talking here about surface modeling in general, but about design situations where surface or quilt-based modeling was used as a workaround to be able to design independent volumes that are not merged automatically, as seen in the video. In those situations, working with surfaces typically requires the creation of more features, and it requires also to switch to a different set of surface and quilt based tools or commands like trim or merge. It can also come with some limitations. For example, you can't drill a hole into a surface quilt. So for those cases, using solid bodies in combination with Boolean and split operations requires less features, less expert knowledge, less switching between solid and surface modeling tools, and allows for reduced modeling time with more intuitive and easier design solutions. This also makes the ramp up easier for new Creo users learning the tool. Multibody concepts also allow for more flexible design intent changes on native or imported parts, as illustrated here. Splitting the body into several pieces and then leveraging Creo's powerful flexible modeling capabilities on those geometric bodies significantly broadens the flexibility you have to perform dramatic design intent changes quickly and efficiently. Again, you might want to note how the geometric search tool as well as the geometric move operation along with its tangency control behavior can work on geometry of multiple bodies. Next, I want to show you a demo that illustrates a bit more how flexible modeling in combination with multi-body design can be used even for not only imported but also native designs. In this case, the key design goal here will be to design this multi-body part as illustrated here, and in particular we want to focus on designing the required shape of that cutout that is being driven by on one hand the arm body and the maximum and minimum angle that this yellow arm is allowed to move within that range. Okay, what I wanted to show you with this demonstration is the usage of some flex modeling tools for the design of parts with bodies. In this example, I have the cylinder body in blue here, and we also have the yellow arm body. And the idea is to first place the arm onto that axis and then define the opening based on the parameterized range of angle values and create the corresponding cutout. Note that I have the long axis here and the small axis defined by the original sketch that contained a point, so that we can use that as a placement axis and reference the positions of arm and cylinder respectively. In order to do that with enough freedom, I will now create a copy of the arm body. This will allow us to modify the volume we need for the cutout independently of the arm, but derive it from the basic shape of the arm. So we call this now arm for cutout. As you can see, if we now turned on cross-section interference, we of course see full interference between the arm and the arm for cutout body, simply because they are representing one-to-one copies overlaid on top of each other. Now what we're going to do is apply a clearance offset onto the shape of the cutout body. To do that, I use the select all body surfaces option and use flex modeling offset of 0.5, for example, to create the offset. That should give us a difference now, as the interference is only matching to the size of the original arm body, and we now have a gray shell frame border around it due to our offset we just applied. Okay, in the next step we are going to position both bodies with move using constraints. You see the bodies are automatically collected to the move object reference collector, to which I also want to add the small axis, which will help us with positioning, and then we'll go to placement and set the two axes coincident. This allowed me to position both bodies, the arm and the arm for cutout, with a single move operation. And now I want to further refine my cutout body. We start with a rotational move upwards, rotated it around the axis and specify the maximum upper angle. Then we repeat the operation, move the arm down, and this time we'll rotate downwards, and we'll need to define this as the maximum upper angle plus the maximum down angle feature relationship as well here. And as I want the upper geometry to stay, I turn on the copy move option. Okay, so that gave us the lower position of the arm for cutout as well, and you might probably guess what we are going to do next. We will fill the space between the gray arms with geometry to get to something that resembles and is close to somewhat like a motion envelope of our last move operation. So we made it the default body, isolated it from the rest, and now we create a sketch and extrude that will define geometry that fills the space and can serve to represent somewhat the motion envelope for that cutout. This now results in the body we can subtract from our cylinder. By default, the modifying body would be consumed in the Boolean operation, Boolean subtract, but in this case I might want to keep it for visualization purposes. And now you see that the movement of the copied arm body gives us the exact shape of the cutout that we needed with the clearance that we defined through the additional offset feature. And of course, if I now change the parameter values and change the max upper angle to a lower value such as 25, I will get a smaller cutout upon regeneration. And again, setting the value to a higher number such as 45 increases the cutout accordingly. Okay, we have already seen quite a number of examples, but there are many more use cases that can benefit from multi-body support. Data exchange is an additional one that I wanted to highlight, where multi-body support streamlines the workflow to import multi-body models from or export models to other CAD systems that support a multi-body concept as well. And while it is a fundamental design concept, we made sure to expose multi-body in Creo in a way that eases the adoption of those new capabilities by making sure previously supported workflows are being preserved. Finally, I want to show how multi-body concepts in Creo 7 relate to the enhanced support of the master model methodology. With this method, you can design bodies in the context of the master model and then extract them into individual parts of your final assembly. This is particularly useful if you have continuous shapes between parts, such as the 3D thread of the clamp parts illustrated here. In addition, part design in context can help to reduce referencing complexity for small assemblies that are driven by a common shape or context. Here, the typical workflow of the master model methodology. This toothbrush example shows a multi-body master model on the left side containing a number of bodies designed in the context of the master model part. These bodies can then be extracted to separate parts and assembled into the final toothbrush assembly. The final assembly would then be a regular assembly with parts being individual business objects listed in the bill of material. Due to the supported associativity and update control capabilities, changes made in the master model can then be propagated to the final parts in the assembly. It is important to note that the bodies designed in the master model don't necessarily have to be fully detailed out in that context. In the scenario illustrated here, the pinkish body was designed in context of the white support body and used to create the cutout into which the final sheet metal bracket is supposed to slide in. In Creo 7, we can now extract that pinkish body, representing the space claim, as a starting point to fully detail out the sheet metal part. In this case, we start with a construction body extracted from a master model part that represents the space claim for the final sheet metal bracket. This body, as well as the copied body that will become the sheet metal bracket, so far still reside in a regular geometry part. You can now convert a selected single basic solid body to a sheet metal body, identified by a body icon colored in green. In addition to the body conversion, the entire part is converted to a sheet metal part during this operation. Now, sheet metal specific commands such as edge rip, join or edge bend can be used to further design the sheet metal body. As a quick intermediate test whether the sheet metal geometry still respects the maximum space claim defined by the original construction body, we can use Boolean operations to subtract the construction body from the sheet metal bracket body. For the test to be successful, this operation needs to entirely consume the geometry and the remaining volume of the sheet metal body should be 0. Note that in addition to the Model tab, there is a Sheet Metal tab. New and existing commands dedicated to interacting with sheet metal and solid bodies are provided in the Sheet Metal tab and the Model tab respectively. Use the tools from the Sheet Metal tab to further refine the sheet metal bracket design. To best represent this distinction, some tools had been refined or added, such as the extruded cut tool used here. A multi-body part in the sheet metal environment can contain a single body of the category sheet metal and optionally multiple bodies of the category basic solid. That means you can work with a sheet metal body in context of other regular geometric bodies. These can represent construction bodies as illustrated so far, or be regular bodies of type basic solid. They can be created within the sheet metal part design environment or inserted using data sharing features such as external copy geometry. The external copy geometry tool offers a follow surface option. Select the follow surface checkbox so that inserted bodies follow the bend and unbend operations on the sheet metal body. Unfold and flatten operations themselves only apply to the sheet metal body though. Use the Boolean operation subtract to subtract geometry of the selected basic solid bodies from the sheet metal body. As you can see, using multibody, it's easier and there's more flexibility when designing sheet metal parts in their design context. This reduces complexity by avoiding external or circular referencing, with the freedom to define space claim and to detail the derived parts. Okay, so this concludes the illustrations and demo videos of the new capabilities in Creo 7 that I wanted to illustrate today. I created this slide in addition to make sure you are all aware of the multi-body related information we provided with the release. If you want to learn more, please have a look at the multi-body What's New pages within the Creo help on the web, which provides documentation and use case based videos and illustrations of the new capabilities. In addition, please note that this also includes 7 tutorials around multi-body use cases, including my demo models that you can download to follow detailed tutorial steps guiding through those workflows. To sum it up, we're very excited about the new multi-body capabilities introduced in Creo 7. I hope I could give you a good overview and introduction into the broad range of use cases that it can support and the benefits that can come with it. Multi-body capabilities are accessible when using the Creo base license, so every user can benefit from them. So far, we have received very positive feedback from customers that started to look at multi-body capabilities in the beta program, and we're really looking forward to seeing them being adopted and used by all of you, many Creo customers that adopt the Creo 7 release. And also the initial reviews in the press had been very positive. If you haven't read the article from Aldine yet, then I would recommend you to do so. It's definitely worth it and a good external review of the Creo 7 release. And then a reminder for every session, please provide session feedback. Your feedback really provides us with valuable information on how to improve the event and how to shape future content strategy for the event. In addition, I also wanted to point you to an activity of the PTC user group and help them promote the planned TC open house sessions. As outlined here, they are scheduled throughout June 10th and 11th and allow interested users of PTC products to learn about the topics that the technical committees are discussing and working with PTC. These groups are always looking to expand membership, so if this is of interest to you, you might want to consider joining the user group. So with that, I would like to close the presentation today. We are really excited about Creo 7. It's fun to see the new multi-body capabilities and the big range of use cases that we cover, and we are really keen in seeing it in your hands in productive use and getting the feedback from productive usage. If you have any questions or feedback on the multi-body capabilities, please contact me. Don't hesitate. Contact me at Neumueller@ptc.com. And then you might also want to check out my multi-body blog on the Creo community pages, where my plan is to add some technical tips and tricks and details on a regular basis to give everyone deeper insights into the multi-body usage details. And with that, thank you very much for your attention and stay safe.